Hello, dear students. I'm your math teacher, Mudassir Ahmed. Let's start our first topic, real numbers. Real numbers. The set of all rational and irrational numbers are known as real numbers. For example, minus 2, minus 1, 0, 1, 2, 3, so on. Rational numbers. Those numbers which are in the form of p by q, where p and q are integers and q is not equal to 0. Rational numbers are terminating or non-terminating repeating decimals. For example, 1 by 2, 2, 3, 2.56, 1.21, 21, 21, dash dash dash. Here 2.56 is a terminating decimal and 1.212121 is a non-terminating repeating decimal because 21, 21, 21 is repeated again and again. Rational numbers. Those numbers which are not in the form of p by q. Rational numbers are non-terminating, non-repeating decimals. For example, 1.01001001001, so on, root 3, root 5. All non-terminating, non-repeating decimals are rational numbers, and the square root of all positive numbers are rational numbers except those which are perfect squares. Now move on the next slide. Euclid's division algorithm. If a and b are two positive integers, then they must satisfy the condition a is equal to bq plus r. Why? 0 is less or equal to r and r is less than b. Here a is a dividend, b is divisor, q is quotient and r is remainder. Remainder is always equal to 0 or greater than 0. It can never be less than 0. Algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Lemma. Lemma is a proven statement used for proving another statement. Fundamental form of arithmetics. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Move on, next slide. How to find HCF using Euclid's division method. HCF of any two positive integers a and b with a is greater than b is obtained as follows. Step first. Apply Euclid's division lemma to a and b to find q and r such that a is equal to bq plus r, 0 is less or equal to r, less than b. B is a divisor, q is quotient and r is remainder. Step second. If r is equal to 0, Then SCF of A and B is equal to B. If R is not equal to 0, you have to apply the equilibrium lemma to B and R. Step 3. Continue the process till the remainder becomes 0. The divisor at this stage will be the required SCF. Turn on next slide. Example, using equilibrium algorithm to find SCF of 135 and 225. Solution. Since 225 is greater than 135, we apply the division lemma to 225 and 135 to obtain 225 is equal to 135 into 1 plus 90. Here A is 225, B is 135, Q is 1 and R is 90. Since remainder 90 is not equal to 0, we apply the division lemma to 135 and 90 to obtain 135 is equal to 90 into 1 plus 45. We consider the new divisor 90 and the new remainder 45 and apply the division lemma to obtain 90 is equal to 45 into 2 plus 0. Since the remainder here is 0, the process stops. Since the divisor at this stage is 45, therefore the SCF of 135 and 225 is 45. More next slide. Example, use equilibrium lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Solution. Let a be any positive integer and b is equal to 3. Then a is equal to 3q plus r for some integer q is greater or equal to 0 and r is equal to 0, 1, 2 because 0 is less or equal to r is less than 3. If our remainder is equal to 0, then a is equal to 3q. Here a is simply a positive integer. We have to show that the square of any positive integer. Now we will squaring both sides. It becomes a square is equal to 3q ka whole square, which is equal to a square is equal to 3 into 3q ka square. Here 3 into 3q ka square is in the form of 3m, while m is equal to 3q square. Now if our remainder is equal to 1, then a must be equal to 3q plus 1. Again squaring both sides, it becomes a square is equal to 3q plus 1 ka square. That is equal to a square is equal to, here 3 plus 1 ka whole square becomes an identity. It's a plus b ka whole square. That is equal to a square plus b square plus 2ab. Instead of a, here it is 3q, and instead of b, here it is 1. Then it becomes 3q ka whole square plus 1 square plus 2ab. That's 2 into 3q into 1. That is equal to 3 into 3q square plus 2 into 3q into 1 plus 1. Now take a common 3 here. It becomes 3 into 3q square plus 2q plus 1, which is in the form of a 3m plus 1, where m is equal to 3q square plus 2q. Thank you. Have a nice day.